This is problem 2.5 from Klein's Organic Chemistry textbook, second edition. They tell us for each of the following molecules, determine the number of carbon atoms present, and then determine the number of hydrogen atoms connected to each carbon atom. So just remember that each carbon needs to have a total of 4 bonds. Any missing bonds should be to hydrogen. And I think the best way to do this problem is just to annotate right on top of these structures. And if you want to jump ahead to part A or B or C or D or E, check my description in the video below. And also consider searching structures on my channel. I have each structure listed on my videos, and you can just jump right to the video of choice. So so let's draw the C's here. So remember, any end of a line or any intersection should be a carbon atom. And then remember that all carbon atoms must have 4 total bonds to it. So this carbon here needs 3 H's. This carbon here needs 3 hydrogens as well. Okay. And this carbon here is done. That one's done. So this one needs 2. This one needs 2. This one needs 2. This one needs 2. Okay. So just to overemphasize and explain here, this carbon here has a total of 4 lines or 4 total bonds to it. Remember, the double bond is counted as 4, so it has 4 bonds total to it, so we don't need to add hydrogens. Here's part B. So again, we'll just annotate right on top of these structures. Any intersection or end of a line is a carbon atom. Don't worry about the oxygen or nitrogen at all here. And we'll go ahead, oops, I like to use this brighter green. We'll add enough hydrogens to each of these carbons to create 4 total bonds to it. Okay, so this one needs 2. This one needs 2. And this one needs 3. Now, how about that carbon atom that I skipped? Well, if we count the total number of bonds to it, remember that carbon needs 4 total bonds to it, and this one has 4 total bonds, so we don't need to add H's to that. Here's part C. Again, any end of a line is a carbon. Any intersection or bend is a carbon. And then we want to add enough hydrogens to complete the tetravalency of carbon. Carbon needs a total of 4 bonds always. So those missing bonds are always to hydrogen. And so these guys on the end need 3 more bonds to hydrogen to complete the octet. These guys here need 2. Okay. And this guy here needs 2. Now this carbon here has 3 bonds to it, so it just needs a 4th or 1 to a hydrogen. Okay. Here's D. So remember, any end of a line is a carbon atom. And any intersection is a carbon atom. And then recall that carbon needs a total of 4 bonds. So we're going to need to add 3 hydrogens to this carbon at the end. And we're going to need to add 3 hydrogens here, and so on. We keep doing this. So these bond line structures never show hydrogen. You need to assume that the missing bonds are to hydrogen, and we're done. Now let me explain why we're done. Let's pick on this carbon here. It's got 1, 2, 3, 4 bonds to it, and so it's not missing any bonds to hydrogen. Every carbon wants 4 bonds, and that has 4 total bonds. Okay. Here's a problem. So let's go ahead and fill in the missing carbons. So each intersection, each bend of a line is a carbon atom. And then now we want to make each carbon have 4 bonds by drawing bonds to the missing hydrogens that are implied by the line structures. And so we're adding all of those in. So all of these carbons now are going to have 4 bonds. Now this one that forms in the middle of this triangle has 3 bonds to it, so we just are missing 1 bond, and we're done. Now this other carbon that I didn't mention, if you carefully count how many bonds it has a total of 4 bonds. The double bond counts as 2 bonds. So that's 1, 2, 3, 4 bonds to carbon, so it's satisfied in terms of its octet. So we don't need to draw any H's there. Okay? Here's part F. So again, any intersection and any bend is going to be a carbon atom. And then because carbon likes to have a total of 4 bonds, we want to draw in those missing bonds to hydrogen. So this needs 2 hydrogens. This needs 2 hydrogens. This needs 2 hydrogens. This carbon here needs 2 hydrogens. And we're done. Now this carbon atom in the middle here doesn't need hydrogens, because if you count the total number of bonds to that carbon atom, we see that it has 4 total bonds, so it has an octet. We don't need to draw any bonds to hydrogen. Here's letter G. So remember, any intersection and any bend in the chain is going to be a carbon atom. And then we want to count the bonds and add any missing hydrogens. So carbon always wants to have 4 bonds. So we're going to need 2 bonds here, 2 additional bonds to hydrogen here, 2 additional bonds to hydrogen here. Now when you're counting these double bonds, you want to count them twice. So here's 1 bond, 2, 3. So this carbon needs a 4th bond. This carbon has 1, 2, 3. It needs a 4th bond there, and we're done. Now if you look at the carbon atom on the top, this carbon atom has 1 bond, 2 bonds, 3 bonds, 4 bonds. We always count double bonds as 2, right? So this has 4 bonds. It has an octet. It's not missing any bonds to hydrogen. Here's letter H, part H. So remember, any intersection is going to be a carbon atom. And then we didn't want to draw in missing bonds. So carbon always has a total of 4 bonds to it, and you need to count carefully. So there's 1, 2, 3 bonds to this carbon, so it's missing a 4th one here. And you can do that for any of these other ones. You're going to see that it has a total of 3 bonds shown by the original printing in the problem. So it's missing a bond to a hydrogen, okay? So I'm going to go ahead and just do those for the other ones. And then we're done. Now let me explain why this carbon atom at the very top of the ring has no hydrogens. It's because it has 1, 2, 3, 4 total bonds to it. So it has an octet, and it's not missing any bonds to hydrogen. Okay, so that's how you do this part H. I here is a bridge bicyclic system. Now I just want to highlight here that this bond looks like it ends there and it ends there, but actually it's behind. Okay, it's behind this bond here, so that's why it's broken. Okay, it goes behind. Okay, if I was holding a large ruler behind me, it would look like the ruler is in 2 pieces. I could see part on the left of me and part on the right of me, but it's going behind my back. You can't see it, right? So when we add carbons, you just add them at the ends of the lines or at the intersections, but don't worry about where I'm pointing those 2 arrows to. That's just an optical illusion of the bridge bicyclic system, okay? So Here we have all the C's written. And remember again, what you want to do is complete the tetravalency of carbon, or complete the octet, by drawing in all the 4 bonds. So this carbon needs 2, this carbon needs 2, this carbon here in the middle just needs 1 additional bond to have 4 total bonds to carbon. And we'll add all of these hydrogens every which way to get each carbon having 4 bonds. Okay, so that should be it. I didn't miss any carbons, and all carbons have a total of 4 bonds now. All right, here's part J. Now here's another interesting feature when you have alkynes. Because alkynes are sp3 sp hybridized, they're linear, their angles are 180 degrees, and so we don't draw them in the standard zigzag fashion. We draw them in a straight line. So we want to draw carbons at these 2 positions that I'm drawing arrows to, as well as the usual ends of a line and the bends. Okay, this is not a bend, but this is an alkyne, so we want to draw those carbons there. Okay, so watch out for that when you're doing bond line structures. Now what we want to do, again, remember carbon has 4 bonds always, so we want to draw in those missing bonds to hydrogen. Here we need 2 additional bonds to hydrogen to get a total of 4 on that carbon. And here we need 2 hydrogens, and here we need 3. Now all of these carbons have 4 bonds to it, and we're done with the structure. Let me explain why we don't need to do anything with the carbons in the middle of this molecule. If we count carefully, we can see that there's 1, 2, 3, 4 bonds to this carbon atom. So it has an octet already. It's not missing any bonds to hydrogen. Here's another structure, and so again we just start off by any ends of a line is going to be a carbon atom, any intersections are carbon atoms, and any bends in the structure are carbon atoms. Remember, carbon is always tetravalent, so we draw enough tick marks and add in H's to each of the carbons to make sure that they all have 4 bonds to them. So these N guys, those are your CH3 groups, carbon with 3 hydrogens, right? And so they all have 4 bonds. This carbon in the middle only needs 1 additional one. This carbon here, if you count carefully, has 1, 2, 3, and so it needs a 4th bond here. Okay? So this carbon has 1, 2, 3, and so it needs a 4th one here. And so we're done. Just want to emphasize that this carbon here connected to the oxygen with a double bond has 1, 2, 3, 4 bonds to it. So it has an octet. It already has 4 bonds. We don't need to draw any bonds that are missing to hydrogen on that carbon atom. Okay? Here's a weird looking structure. Again, any bend in a chain, any intersection is a carbon atom. So you draw all those in and carefully count to make sure each carbon has 4 bonds. So we need 2 additional bonds here, and we fill those in with hydrogens. We need 2 here. We need 2 here. And we need 2 here. And we need 2 here. Okay. And we're done. This carbon in the middle of this spirofused ring system already has 4 bonds to it, right? So that carbon has 4 bonds to it, and so it doesn't need additional hydrogens to make it have 4 bonds. And if I try to switch my pen to, I don't know, yellow here, this carbon is doubly bonded, so that counts as 2 bonds. It's singly bonded this way and singly bonded this way. So that carbon also has 4 bonds. So we don't need to draw additional bonds to hydrogen to make sure it has an octet. So that structure is now complete. All right. So thanks for watching this video.